Have you ever looked up at the night sky and wondered if there's a hidden order to it all? A kind of cosmic blueprint that holds everything together in perfect, silent harmony. For centuries, scientists, philosophers, and dreamers alike have been captivated by the idea that beneath the apparent chaos of the universe lies a profound and elegant symmetry, an invisible architecture that governs everything from the spin of distant galaxies to the behavior of the tiniest particles. This isn't just an abstract concept, it's one of the most compelling mysteries of existence itself. What if I told you that these hidden symmetries might hold the key to unlocking the deepest secrets of reality, secrets that have remained just out of reach, waiting for the right minds to uncover them? Today, we're embarking on a journey to explore 30 astonishing theories about the universe's hidden symmetry. These aren't just dry scientific ideas, they're gateways to understanding the very fabric of space, time, and matter. Think about it, from the perfect spirals of galaxies to the mathematical beauty of fundamental forces. Symmetry seems to be written into the cosmos in ways we're only beginning to comprehend. It's as if the universe is whispering a code, a language of patterns and connections that hints at a reality far stranger and more magnificent than we ever imagined. And the most thrilling part, we're on the verge of deciphering that code. So whether you're a seasoned science enthusiast or simply curious about the wonders of the cosmos, this exploration is for you. Together, we'll dive into ideas that challenge our perception of everything from the birth of the universe to the nature of consciousness itself. We'll meet the brilliant thinkers who have dared to ask the big questions and follow the clues they've uncovered. This is more than a video. It's an invitation to see the universe in a whole new light, to witness the elegance hidden in plain sight, and to join a conversation that has fascinated humanity for generations. Are you ready to begin? To kick off our journey, we begin with one of the most elegant and compelling ideas in modern physics, supersymmetry, often called SUSY. At its heart, this theory proposes a stunningly beautiful and profound kind of symmetry, a partnership on the most fundamental level. It suggests that for every particle we know exists in the universe, there is a hidden, supersymmetric partner particle waiting to be discovered. Think of it as a cosmic mirror image, a shadow world of particles that balances our own. This isn't just a theoretical fantasy. It's a potential solution to some of the most stubborn puzzles in science. Take, for example, the hierarchy problem. This is the baffling question of why gravity is so unimaginably weaker than the other fundamental forces. The math we use to predict particle masses, particularly the mass of the Higgs boson, suggests the universe should have blown itself apart long ago. The numbers come out astronomically wrong. But supersymmetry elegantly calms this mathematical storm. Those superpartner particles would cancel out the problematic calculations, like a counterweight providing perfect balance, making the universe we see not only possible but stable. Perhaps even more tantalizing is supersymmetry's proposed link to the mystery of dark matter. We know this invisible substance makes up about 85% of all the matter in the cosmos, its gravitational pull holding galaxies together. Yet we have no idea what it actually is. SUSY provides a prime candidate, the lightest of these superpartners. This particle would be stable, neutral, and wouldn't interact with light, fitting the profile of dark matter perfectly. It could be all around us, passing through you right now, a ghostly remnant of the universe's symmetric beginnings. The hunt for these particles is one of the great scientific endeavors of our time, centered at facilities like the Large Hadron Collider. Scientists smash protons together at nearly the speed of light, searching for the tiny energy signatures that would betray a superpartner's fleeting existence. While we haven't found direct evidence yet, the mathematical elegance of SUSY keeps the search alive. It represents a deep hope that the universe operates on principles of profound beauty and order, and that we are close to uncovering a new, symmetrical layer of reality. But if supersymmetry offers a tantalizing glimpse into a hidden layer of particles, Then our next theory asks us to contemplate an even more radical idea, that the very fabric of spacetime is woven from far more threads than we can perceive. This is string theory, a framework that suggests the fundamental constituents of the universe are not point-like particles but unimaginably tiny, vibrating strings. And the pitch and resonance of these vibrations, the theory says, determine whether a string manifests as an electron, a quark, or a photon. It's a beautiful notion that the entire cosmic symphony is played on these infinitesimal instruments. However, for the mathematics of this symphony to work, for the equations to produce the universe we observe, string theory requires something extraordinary, extra dimensions of space. We're all familiar with the 3 dimensions of length, width, and height, plus the dimension of time. But string theory suggests there are 6 or 7 additional spatial dimensions, all curled up into a space so small that a billion of them could fit inside a single atom. This isn't science fiction, it's a necessary consequence of the theory's internal logic. The shape into which these extra dimensions are folded is absolutely critical. It dictates the properties of every particle and the strength of every force in our 4-dimensional world. Imagine a distant flute player. You can't see the intricate design of the instrument, but its precise shape determines the unique sound that reaches your ears. In the same way, the hidden, coiled geometry of these dimensions dictates the laws of physics we experience, and the most promising shapes for this job are known as Calabi-Yau manifolds. These are not simple shapes like spheres or cubes. Calabi-Yau manifolds are complex, multi-dimensional forms with a breathtaking amount of intricate, hole-riddled structure. To say they have mathematical beauty is an understatement. They are objects of profound elegance that exist in the abstract landscape of geometry. Their topology, the number of holes, the twists and folds directly translates into the number of generations of particles, the charges they carry, and even the number of forces in our universe. A differently shaped Calabi-Yau manifold would produce a universe with completely different physics, one where atoms might not even form. This is where string theory's grand ambition truly shines: unification. By describing all particles and forces as different vibrational modes of these fundamental strings, the theory provides a single, elegant framework that naturally includes gravity. In essence, the graviton, the hypothetical particle that carries the gravitational force, is just another note in the vibrational spectrum. This is a monumental step towards the holy grail of physics, a theory of everything that seamlessly weaves together the quantum world with Einstein's general relativity. The Calabi-Yau shape is the key, the hidden geometric lock that, once understood, could unlock a unified understanding of all cosmic forces. But if string theory asks us to imagine unseen dimensions, the holographic principle proposes something even more radical: that our entire experience of a 3-dimensional universe might be nothing more than a magnificent illusion. This is perhaps one of the most profound and counterintuitive ideas to emerge from theoretical physics, suggesting that all the information contained within any volume of space can actually be encoded on its 2-dimensional boundary, like a cosmic projection. Think of a familiar hologram where a 3-dimensional image is stored on a flat, 2-dimensional piece of film. The principle suggests our reality might operate on a similar, albeit vastly more complex, scale. The roots of this astonishing idea are found in the fiery physics of black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, which is a measure of the hidden information or disorder within a system, is not proportional to its volume as one might expect. Instead, it is directly proportional to the surface area of its event horizon. This was a revolutionary insight. It implied that all the information about everything that ever fell into a black hole, every star, every planet, every bit of matter, is somehow painted onto the surface of its boundary. The 3-dimensional interior was being described by a 2-dimensional surface. This connection between information and surface area was solidified by Stephen Hawking's work on Hawking radiation, which showed that black holes are not entirely black but slowly evaporate over astronomical timescales. This raised a terrifying paradox. If a black hole evaporates, what happens to all that information it swallowed? The laws of quantum mechanics insist that information cannot be destroyed, it can only be scrambled. The holographic principle emerged as a potential solution. It posits that the information is never truly lost inside the singularity. It remains forever encoded on the event horizon's surface. The universe, in its most fundamental description, might not need more than 2 dimensions to store all the data required to generate our 4-dimensional experience of spacetime. The implications of this are staggering. It suggests that the world we perceive, with its rich depth and volume, might be a kind of projection, a holographic movie playing out on the distant surface of the universe. Every particle, every force, every event that unfolds within the cosmos could be translated into a vast, complex code written on the 2-dimensional boundary of space itself. You, me, the planet we live on, we would all be incredibly detailed and dynamic expressions of information stored on this fundamental surface. This principle provides a powerful new way to approach the problem of quantum gravity. By describing a gravitational system within a volume in terms of a quantum theory on its boundary, physicists can tackle problems that were previously intractable. It's a duality that allows them to use a well-understood quantum framework without gravity to understand a gravitational system where quantum mechanics normally breaks down. The holographic principle doesn't just challenge our perception of reality. It offers a practical toolkit for unifying the largest and smallest scales of the universe, suggesting that the deepest truths of existence might be written in a simpler, lower-dimensional language than we ever dreamed. Now, if the holographic principle challenges our very perception of reality's dimensions, then our next theory completely reimagines the timeline of the cosmos itself. This is Conformal Cyclic Cosmology, or CCC, a breathtaking vision proposed by the Nobel laureate physicist Sir Roger Penrose. It suggests that our universe is not a one-time event but merely one chapter in an infinite series of cosmic cycles, stretching from an unimaginable past into an endless future. In this grand scheme, the death of one universe becomes the Big Bang of the next, in a cycle of renewal governed by a profound and elegant symmetry. The key to understanding this endless rebirth lies in a specific type of symmetry called conformal symmetry. This is a principle that allows objects to be scaled up or down in size while preserving their angles and shapes. Imagine a detailed map. You can enlarge it or shrink it, and while the scale changes, the precise relationships between cities and landmarks remain intact. Conformal symmetry suggests that the fundamental laws of physics might remain unchanged even as the entire universe stretches to an infinite vastness or shrinks to an infinite smallness. Penrose realized that at the very far future of our universe, and at the very beginning of a new one, this scaling symmetry could effectively erase the concept of scale itself. In this conformal geometry, a universe that has expanded to become nearly empty and cold is mathematically equivalent to a universe that is hot, dense, and incredibly small. This leads to an astonishing conclusion. In the distant future, trillions upon trillions of years from now, our universe will have expanded so much that all matter will have decayed or been sucked into black holes, which will then themselves evaporate away via Hawking radiation. All that will remain is a vast, empty sea of low-energy photons, stretched to wavelengths so long that distance and time lose all meaning. At this point, conformal symmetry takes over. This cold, empty, expanded state can be conformally rescaled to become the hot, dense, contracted state of a new Big Bang. The end of one eon seamlessly becomes the beginning of the next in a transition Penrose calls an eon. There is no singularity, no point of infinite density, just a smooth, conformal reshaping of the cosmos. But what about us? What happens to all the information, the structure, the history of our universe? This is where the theory becomes truly poetic. Penrose proposes that while particles and energy are reset, certain information might be preserved across the boundary between eons through the imprint of gravitational waves. The most dramatic events of our eon, like the collisions of supermassive black holes, would send out ripples in spacetime that would not be erased by the conformal rescaling. These ripples could cross the boundary and manifest as faint, circular patterns in the early plasma of the next universe. Incredibly, Penrose and his colleagues believe they may have found evidence for this in our own universe's infancy. They analyzed the cosmic microwave background, the leftover heat from the Big Bang, and identified strange, concentric circles of slightly higher temperature variation. These Hawking points, as Penrose calls them, could be the imprints of black hole collisions from the eon that came before ours, their gravitational shock waves etched onto the very first light of our cosmos. While this interpretation is still hotly debated within cosmology, it offers a potentially testable prediction for a theory that spans the infinity of time. It suggests that the universe possesses a hidden symmetry so powerful that it allows existence to recycle itself, preserving echoes of its past incarnations and weaving them into the fabric of the new. Yet if the holographic principle gives us a radical new perspective on reality's dimensions, and cyclic cosmology reshapes our view of time, then the next theory provides a concrete, mathematically precise blueprint for how such a holographic universe could actually operate. This is the anti-de Sitter/conformal field theory correspondence, often called the grandest realization of the holographic idea. It proposes a stunning and exact duality. A theory of gravity playing out in a hypothetical warped space is completely equivalent to a special kind of quantum field theory living on its lower dimensional boundary. They are not just similar, they are two utterly different descriptions of the exact same physical reality. To grasp this, we first need to understand the stage, anti-de Sitter space or ADES. Imagine a universe that is not expanding like our own, but is instead curved inward like the surface of a saddle that stretches on forever. This geometry creates a powerful gravitational pull toward the center, making it a contained, self-enclosed system with a distinct boundary at infinity. Now, on this boundary, physicists define a conformal field theory, or CFT. This is a quantum theory that, crucially, has no gravity in it whatsoever. It describes particles and forces interacting on a flat, rigid stage. The miraculous claim of the correspondence is that every single event, every calculation, every prediction you can make in the gravitational ADES universe has a perfect mirror translation in the equations of the quantum CFT on the edge. They are holographic twins. This means an incredibly complex, poorly understood problem in quantum gravity, like figuring out what happens inside a black hole, can be transformed into a much more manageable problem in a well-understood quantum theory without gravity. It's like being given a universal translator for the cosmos. A physicist struggling with the messy mathematics of a collapsing star in the ADES bulk can instead solve a problem about the behavior of particles and heat on the boundary CFT, and the answer will be the same. This has provided unprecedented insights into the infamous black hole information paradox. Using the ADES/CFT dictionary, physicists have been able to show that information is not lost when matter falls into a black hole. It is indeed scrambled and encoded onto the event horizon, preserving it in line with quantum law, just as the holographic principle suggested. The implications of this duality stretch far beyond black holes, offering a powerful new way to understand some of the most perplexing substances in the universe. Take the quark-gluon plasma, a state of matter so incredibly hot and dense that it hasn't existed naturally since the first microseconds after the Big Bang. We can create fleeting glimpses of it in particle colliders, but its properties are extremely difficult to calculate using standard quantum methods. Through the ADS/CFT correspondence, this incredibly complex fluid can be modeled as a black hole in a hypothetical ADS space. The viscosity and entropy of the plasma are directly related to the properties of the black hole's horizon. This has allowed scientists to make precise calculations about this primordial soup, revealing it to be a nearly perfect liquid with astonishingly low friction, a discovery that was both unexpected and deeply insightful. While our own universe appears to be fundamentally different from anti-de Sitter space, we seem to live in a universe that is expanding at an accelerating rate, closer to what's called de Sitter space. The success of the ADS/CFT correspondence is undeniable. It stands as the most rigorously tested example of holography in action, a mathematical gem that demonstrates how the deepest laws of the universe might be written in a language of dualities and correspondences, where gravity and the quantum world are not separate realms but two sides of the same holographic coin. It suggests that to find the answers to our biggest questions, we might not need to look deeper into the void, but rather, we might find them written clearly on the walls of our cosmic cell. But just as the Calabi-Yau manifold provides the hidden geometric stage for string theory, a remarkable discovery revealed that this stage might have a perfect understudy waiting in the wings. This is the concept of mirror symmetry, a breathtakingly elegant mathematical relationship that suggests for certain Calabi-Yau shapes, there exists a mirror partner, a completely different-looking geometry that nonetheless produces the exact same physics. Imagine two entirely different musical instruments, one a violin and the other a flute, that through some strange acoustic magic are capable of playing the exact same symphony. That is the essence of this profound duality. The discovery was almost accidental. While studying the mathematics of string compactification in the late 1980s, physicists found that the calculations for one particular Calabi-Yau shape were unexpectedly simple. Upon closer inspection, they realized the math was identical to that of a far more complex, seemingly unrelated Calabi-Yau manifold. It was as if the universe had provided a shortcut. A problem that was impossibly hard on one geometry became trivially easy when viewed through the lens of its mirror twin. This wasn't just a curiosity, it was a powerful new computational tool. To understand how this works, consider one of the most important numbers a physicist needs to calculate: the number of ways a string can wrap around the holes and loops of a Calabi-Yau manifold. These world-sheet instantons are crucial for determining the properties of the particles we see in our four-dimensional world. On one mirror manifold, calculating these wrapping numbers is a nightmare of complex integrals. But on its mirror partner, the same calculation reduces to a simple problem of counting points in a geometric grid. The two descriptions, though mathematically distinct, are physically equivalent. By switching to the mirror perspective, an intractable problem becomes solvable almost overnight. This symmetry has had a revolutionary impact, bridging two seemingly separate worlds, physics and pure mathematics. A physicist's question about the number of particle generations in a string theory model can be translated into a deeply abstract question about the number of holes in a mirrored manifold, a problem a mathematician might have already solved. This cross-pollination has led to stunning advances in both fields. Mathematicians have used the physical intuition from string theory to prove long-standing conjectures in algebraic geometry, while physicists have gained powerful new methods to explore the vast landscape of possible universes hidden within string theory's equations. Mirror symmetry reveals that at the highest levels of knowledge, the boundaries between disciplines blur, united by a shared language of hidden patterns and elegant correspondences. Now, if mirror symmetry reveals a hidden partnership between geometries, the next theory takes us to the very bedrock of reality itself, to a principle so fundamental that many physicists believe it cannot be broken. This is CFT symmetry, a cornerstone of modern physics that asserts the laws of nature must remain unchanged under the combined transformation of swapping charge, mirroring space, and reversing time. To understand this profound invariance, we need to unpack each of its components and see how they unite into what is arguably the most sacred symmetry in the universe. Let's start with the easiest part to visualize: parity or p-symmetry. This is the idea that the laws of physics should be the same if you take the universe and look at it in a mirror. If you and your mirror image performed an experiment, you should both get the same result. For a long time, this was considered an unshakable truth, but in the 1950s, a stunning discovery by Qin-Xiang Wu shattered this assumption. Through meticulous experiments with radioactive cobalt-60, she showed that the weak nuclear force, the force responsible for nuclear decay, actually distinguishes between left and right. In the mirror universe, the experiment would yield a different outcome. Parity was not just violated, it was maximally violated. The universe on a fundamental level has a handedness. Next, we have charge conjugation, or C-symmetry. This is the idea that you could swap every particle with its antiparticle electrons with positrons, protons with antiprotons, and physics should proceed exactly as before. It's a swap of matter for antimatter, but just like parity, this symmetry was found to be broken by the weak force. A world made entirely of antimatter would not behave identically to our own. Now here's where it gets fascinating. For a brief moment, it seemed the universe was deeply biased, but then physicists discovered that if you combine these two broken symmetries, if you simultaneously mirror the universe and swap matter for antimatter, the laws of physics are restored. This combined CP symmetry seemed to hold. That is, until 1964, when James Cronin and Val Fitch made another earth-shattering discovery. They found that even CP symmetry could be violated in the decays of certain particles called kaons. This was a monumental shock to physics, as it implied a fundamental difference between matter and antimatter that went even deeper, helping to explain why our universe is made almost entirely of matter despite both being created in equal amounts at the Big Bang. So if C, P, and even CP can be violated, what's left? This is where the final piece, time reversal or T-symmetry, enters the picture. This principle suggests that if you were to run time backwards, the laws of physics should still hold. A movie of two billiard balls colliding should look physically plausible whether played forwards or backwards. While certain microscopic processes show a clear arrow of time, most fundamental laws are time reversal invariant. Now here is the miraculous part. While C, P, and T can each be violated individually, and even CP can be violated, there is a profound and robust theorem in quantum field theory that states that the combined operation of all three CPT must always be an exact symmetry of nature. This is the CPT theorem, and it is not just a good idea. It's a foundational requirement that emerges from the very principles of relativity and quantum mechanics, specifically Lorentz invariance. This theorem is so powerful that it is often considered the one absolute symmetry that cannot be broken. The implications of this are staggering. Because of CPT symmetry, a particle and its antiparticle must have exactly the same mass and the same lifetime. It's why we can be so confident that the spectra of light from distant antimatter galaxies would look identical to those from matter galaxies. This symmetry also provides a profound connection to the nature of time itself. A violation of CPT would be equivalent to a violation of Lorentz invariance, shaking the very foundations of Einstein's relativity. For this reason, experimental physicists are constantly testing the limits of CPT invariance, comparing the magnetic moments of protons and antiprotons with incredible precision, searching for any tiny discrepancy. So far, none has been found. This unbreakable symmetry stands as a silent guardian of cosmic order, ensuring that beneath all the apparent violations and asymmetries, the universe retains a perfect, deeper balance. But to truly appreciate the universe's hidden architecture, we must also consider a symmetry that isn't about flipping or reversing, but about scaling. Imagine zooming in on a photograph, expecting the image to eventually break down into a blur of pixels, only to find the same intricate patterns repeating at every magnification. This self-similarity is a hallmark of scale invariance, a beautiful symmetry where the laws of physics remain unchanged regardless of how much you zoom in or out. And while it might sound abstract, this phenomenon is the key to understanding some of the most dramatic transformations in nature, from the freezing of water to the birth of the cosmos itself. This symmetry emerges most perfectly at a concept known as a critical point. Think of a pot of water coming to a boil. As it heats up, tiny bubbles form, merge, and pop in a chaotic dance. Right at the moment it transitions from liquid to gas, at the critical point something extraordinary happens. These bubbles and fluctuations appear at every conceivable size, from the microscopic to the pot-sized. The system has no preferred scale. It looks the same whether you observe it from an inch away or from across the room. It is, for that fleeting moment, scale invariant. The physics governing a tiny bubble is identical to the physics governing a large one. This isn't just a kitchen phenomenon. It appears in the most unexpected places, like the precise alignment of atoms in a magnet. When a piece of iron is heated to its specific critical temperature, its magnetic domains fluctuate in a self-similar fractal pattern. The magnetic field fluctuates at all scales simultaneously, creating a state of perfect tension between order and chaos. This critical state is incredibly delicate, balanced on a knife's edge, which is why it's so rare and powerful in everyday life. But what if the universe itself went through such a critical phase transition in its earliest moments? This is where cosmology takes a profound lesson from condensed matter physics. The leading theory for the universe's exponential expansion, known as cosmic inflation, proposes that the infant cosmos did indeed experience a version of this critical phenomenon. During this incredibly brief but pivotal period, the universe was perched at a similar point of instability, causing quantum fluctuations in the inflatoned field to be stretched across astronomical distances. Because inflation occurred at this critical point, these fluctuations were born with scale invariance stamped into their very nature. The tiny quantum jitters that seeded all future structure, the galaxies, clusters, and vast cosmic voids were imprinted with no preferred scale. The evidence for this is written in the oldest light we can see, the cosmic microwave background. When we map the minute temperature variations in this afterglow of the Big Bang, we find a pattern that is almost, but not perfectly, scale invariant. The fluctuations in the density of the early universe appear with nearly equal strength across all measurable scales, just as the theory of inflation predicts. This breathtaking correspondence suggests that the largest structures we see in the universe today, the great web of galaxies stretching across billions of light years, originated from subatomic quantum fluctuations, magnified and frozen into the cosmos by a period of critical scale symmetric expansion. It is one of the most elegant connections in all of science, linking the infinitesimally small to the astronomically large through a hidden symmetry of scale. Yet while scale invariance reveals a pattern woven into the very fabric of cosmic expansion, another profound idea seeks to unify the fundamental forces that govern that fabric. For centuries, physicists have pursued a dream of unification, a single, elegant framework that could describe all of nature's forces. We've already seen how electromagnetism and the weak nuclear force unite into the electroweak force at high energies. But what if we could go further? This brings us to grand unified theories, or GUTS, ambitious blueprints that aim to weave the electroweak force and the strong nuclear force into a single, majestic tapestry. The driving principle behind this monumental effort is once again symmetry. Think of the fundamental forces as different languages. At the low energies of our everyday world, they seem completely distinct, like someone speaking English, another Mandarin, and a third Arabic. But a grand unified theory proposes that these are merely dialects. If you could turn up the energy equivalent to turning back the clock to a searingly hot moment just after the Big Bang, these differences would melt away, revealing one underlying universal language of nature. The forces would merge into one, governed by a larger, more beautiful symmetry. The mathematics behind this is where the true elegance lies. The strong force is described by a symmetry group called SU3, while the electroweak force uses SU2 times U1. A GUT posits that both of these groups are actually just subsets of a much larger, overarching symmetry group, like branches stemming from a single tree trunk. The most famous early candidate was the SU5 model. This theory elegantly packaged all the known fermions, the quarks and leptons that make up matter, into neat families. It predicted thrilling new phenomena, most notably that the proton, long thought to be perfectly stable, should actually decay over immense timescales. This prediction of proton decay is a cornerstone of experimental tests for GUTS. If true, it means that the atoms we are made of are not permanent. Given enough time, the protons in every nucleus will spontaneously transform, spitting out a positron and turning into a pure burst of energy. The estimated half-life for this process is staggering, around 10 to the 34 years. To test this, scientists have built enormous detectors deep underground, like Supersymmetry, and in Japan, a tank containing 50,000 tons of ultra-pure water, surrounded by incredibly sensitive light sensors. They wait in perfect silence, watching for the telltale flash of light that would signal the death of a single proton. While we haven't seen definitive evidence yet, the search continues, pushing our detectors to ever greater levels of sensitivity. The SU5 model, while beautiful, ran into some problems, particularly with the predicted rate of proton decay being faster than what we observe. This led physicists to explore even larger symmetry groups like SO10. This model is even more compelling, as it naturally incorporates all the fermions of a single generation into one 16-dimensional representation. It also elegantly includes a right-handed neutrino, a particle that could explain the tiny masses of neutrinos and might even be a key component of dark matter. SO10 doesn't just unify forces, it provides a more complete picture of matter itself. A critical concept in all these theories is symmetry breaking. Imagine a perfectly spherical ball sitting on the top of a sombrero. This represents the universe in its hot, early state, full of symmetry, but this position is unstable. The ball will eventually roll down into the brim of the hat, choosing one specific direction and settling into a lower energy state. In doing so, the perfect spherical symmetry is broken. This is what happened as our universe expanded and cooled. The grand unified symmetry broke, and in that breaking, the single primordial force differentiated into the distinct strong and electroweak forces we observe today. This phase transition would have been a violent event, possibly creating cosmic strings or other exotic defects in spacetime that could still be echoing through the cosmos today. The pursuit of grand unification represents one of the most daring quests in all of science. It's a search for a deeper harmony, a conviction that beneath the apparent complexity of our universe's laws lies a stunning simplicity. While the energy scales required to test these ideas directly are far beyond the reach of any particle collider we can build, the indirect evidence, from proton decay searches to the properties of neutrinos, guides us forward. These theories challenge us to think on the grandest of scales, connecting the destiny of every proton to the fiery birth of the cosmos itself. This profound imbalance between matter and antimatter in our universe is one of the most pressing mysteries in all of cosmology. We call this the problem of baryon asymmetry. If the Big Bang had created equal amounts of matter and antimatter, as our most fundamental symmetries suggest it should have, the two would have completely annihilated each other, leaving behind a cosmos filled with nothing but light. The fact that we exist, that stars and planets and galaxies are made of matter, is direct evidence that something broke that perfect symmetry in the early universe, allowing a tiny 1 in a billion excess of matter to survive. The question is, what? In the 1960s, the brilliant Soviet physicist and dissident Andrei Sakharov provided the essential answer. He outlined 3 necessary conditions that must be satisfied for any universe to generate more matter than antimatter, a process we call baryogenesis. These are now known as the Sakharov conditions, and they form a breathtakingly elegant recipe for existence itself. The first condition seems almost too obvious. The universe must violate baryon number conservation. A baryon is a heavy particle like a proton or neutron, the building blocks of atoms. For a long time, it was thought that the total number of baryons in the universe could never change. You couldn't create or destroy this brick of matter. But if that were strictly true, the universe would have started with a set number of baryons and antibaryons, and they would have all annihilated. Sakharov realized there must be processes in the early, high-energy universe that can actually create a net baryon number from nothing, effectively allowing the universe to have a preference for matter. His second condition is a departure from thermal equilibrium. Imagine a perfectly calm, hot soup of particles and radiation where everything is in balance. In such a state, any process that creates a slight excess of matter would be immediately countered by its reverse process, which would create an equal excess of antimatter, cancelling out any gain. For the universe to make a decision and tip the scales, it had to go through a phase where it was out of balance, a sudden, dramatic event like a phase transition where the reactions couldn't keep up, effectively freezing in a tiny surplus of matter before nature could correct the error. The third, and perhaps most famous, condition is the violation of both C and CP symmetry. As we discussed earlier, this means the laws of physics must treat particles and antiparticles differently, and they must also treat the mirrored versions of those reactions differently. This is the cosmic bias we need. If matter and antimatter behaved exactly the same way in all circumstances, any process that created 1 extra particle of matter would invariably create 1 extra particle of antimatter, again resulting in a perfect zero. CP violation provides the mechanism for a one-way street, allowing the universe to favor the production of, say, a quark over an antiquark by the tiniest of margins. We have observed CP violation in the laboratory, specifically in the behavior of quarks, but the amount we've seen is far too small to account for the vast amount of matter we see in the cosmos today. This tells us that the CP violation we've found in quark decays is likely just a small piece of a much larger puzzle. The true source of the universe's matter bias might lie in processes we haven't yet observed, perhaps involving the mysterious neutrinos or even more exotic particles from the grand unification epoch. The hunt is on to find new, stronger sources of CP violation, as they would not only explain our existence but could also be a direct window into physics at energy scales we can never hope to recreate on Earth. The emptiness of space, the glow of distant galaxies, and the very atoms in our bodies are all testament to an ancient, broken symmetry that made everything possible. But this breathtaking fine-tuning of the cosmos leads us to a deeply puzzling question. Why do these constants have the precise, life-permitting values that they do? One compelling answer suggests that the very concept of a why might be a question for a single universe, but we may actually be part of a much vaster and more varied cosmic archipelago. This is the anthropic principle, an idea that shifts the perspective from why our universe is fit for life to the realization that we can only observe a universe that is fit for us. It's a selection effect of the most profound kind, and when combined with the concept of the multiverse, it points toward a breathtaking form of symmetry on a grander scale. Think of it like this. Imagine you are a fish that has spent its entire life in a pond. You might perform experiments and conclude that the laws of physics mandate that water is a fundamental property of the entire world. It would never occur to you that other environments, like deserts or forests, even exist. your perspective is limited by your own existence. In the same way, we are cognitive creatures who evolved in a universe with specific constants. We are, in a sense, prisoners of our own environment, and we shouldn't be surprised to find that the universe we inhabit is one that allows for our existence. The anthropic principle isn't so much an explanation as it is a logical constraint on our observations. Now, to transform this from a philosophical constraint into a physical theory, we need a mechanism that can generate a vast number of different environments. This is where the multiverse concept and the string theory landscape provide a powerful synergy. As we explored earlier, string theory suggests the existence of perhaps 10 to the 500 or more possible vacuum states, each corresponding to a different way the extra dimensions can be curled up. Each of these configurations results in a different set of physical laws and constants. In this landscape of possibilities, our universe is just one tiny plot of land with the right conditions for life. Countless other universes exist where the electrons are too heavy, the strong force is too weak, or the cosmological constant is so large that space tears itself apart before stars can ever form. In those universes, there is no one to ask why the constant seems so fine-tuned. This is where we see a magnificent restoration of symmetry, but not within a single universe. The symmetry exists across the entire multiverse, while the symmetry of a grand unified theory is broken within our particular bubble of space-time, giving us the forces we see. The higher dimensional symmetry of the underlying theory remains intact across the entire landscape. Every possible breaking pattern, every possible set of laws is realized somewhere. The apparent fine-tuning in our universe is not a miracle. It is simply a consequence of probability played out across an almost infinite canvas. We don't live in a specially designed universe. We live in a typical one among the subset that can support conscious life. This idea finds a powerful analogy in the process of biological evolution. On Earth, the development of the eye occurred independently several times. While the specific structure of a human eye, an octopus eye, and a fly's eye are all different, they all converged on a solution for detecting light because it was a useful adaptation in their environment. The environment selected for this trait, in the cosmic context, the multiverse is the environment, and it selects for universes that can produce complex structures and observers. The why is answered by a form of cosmic natural selection, where the observed constants are the ones that allow for the observers who do the observing. Critics often argue that the multiverse explanation is untestable and therefore unscientific. How can we ever prove the existence of universes we cannot interact with? Proponents, however, point to indirect evidence. If a specific theory, like inflation or string theory, which predicts a multiverse, continues to be supported by evidence within our own universe, such as the precise pattern of the cosmic microwave background or the discovery of supersymmetry, then the multiverse becomes a natural and plausible consequence of that well-supported physics. We may never see another universe, but we might become increasingly confident that our own is just one leaf on a vast cosmic tree, its particular shape explained not by destiny, but by a hidden symmetry woven into the fabric of all reality. While the multiverse paints a picture of infinite possibilities, other theories aim for a single, ultimate equation to describe our one universe. This brings us to a theory of breathtaking mathematical beauty and deep controversy, known as the exceptionally simple theory of everything, proposed by the physicist and surfer Garrett Lissy. His radical idea suggests that the entire universe of particles and forces, including gravity, can be perfectly arranged within the intricate geometry of the largest simple exceptional Lie group known as E8. To grasp the ambition here, picture a grand, multi-dimensional snowflake of unimaginable complexity. A Lie group is a mathematical structure that describes continuous symmetries, and E8 is perhaps the most majestic of them all. It is a 57-dimensional object with 248 dimensions of symmetry, a pattern so vast and intricate that mapping its full structure was a mathematical challenge that took decades to complete. Lisey's profound insight was to propose that every single element of this abstract geometry corresponds directly to a known or predicted particle in the universe. In this model, an electron, a quark, a photon, and even the graviton are not independent entities. They are merely different facets of this one perfect, symmetric shape. The theory's elegance is staggering. By placing the known particles of the standard model and the proposed carriers of gravity into specific positions within the E8 structure, their properties, their charges, their spins, their masses are no longer arbitrary numbers to be measured in lab. Instead, they emerge naturally from the geometric relationships they have to one another within the group. It's as if the universe's entire particle content were a single, solved jigsaw puzzle, and E8 is the picture on the box showing how every piece fits together in perfect harmony. This approach bypasses the need for the extra dimensions of string theory, proposing instead that all of reality's complexity is encoded in the intrinsic properties of this one mathematical object. However, for all its captivating beauty, the theory faces monumental challenges when confronted with experimental data. The most significant hurdle is the generation of particle masses. In the standard model, particles acquire their mass through interactions with the Higgs field, a process known as the Higgs mechanism. For Lisey's theory to work, it must naturally incorporate a similar mechanism that gives each particle its correct mass directly from the E8 symmetry breaking. So far, generating the specific and wildly different masses we observe from the almost weightless electron neutrino to the incredibly heavy top quark has proven to be an extremely difficult task within the framework, and critics argue that the model in its current form lacks a natural way to do this. Furthermore, the theory makes specific predictions that have not been borne out by experiments at the Large Hadron Collider. A key feature of the model is that it does not include a fundamental Higgs boson as a separate entity. Instead, the Higgs is meant to be a composite particle made up of other prions in the theory. The triumphant discovery of the Higgs boson in 2012, with properties that align perfectly with the predictions of the standard model, was a serious blow to the original formulation of Lisey's idea. While the theory can be adjusted to include a Higgs-like particle, these adjustments can begin to erode the very simplicity that made the proposal so compelling in the first place. Despite these formidable obstacles, the E8 theory remains a fascinating and inspirational what-if in theoretical physics. It stands as a powerful testament to the human desire to find ultimate order and elegance in nature, a modern-day Pythagorean belief that the universe is fundamentally mathematical and musical in its structure. It challenges the physics community to consider more audacious, geometrically driven approaches to unification, even if the primary legacy of E8 is to remind us that any final theory must possess not only magnificent beauty, but also the gritty, concrete ability to predict the world as we actually find it. But what if our entire conception of spacetime is backwards? We've been exploring theories that add hidden dimensions or propose holographic projections. But what if the very points that make up space and time are not the fundamental building blocks? This brings us to a truly mind-bending alternative pioneered by the legendary mathematician and physicist Roger Penrose. It's called twistor theory, and it turns our standard view of physics completely on its head. Instead of starting with points in space and time and then building up particles and forces, Penrose's radical idea suggests that spacetime itself emerges from something deeper and more primitive: twistors. Think of it this way: for centuries we've described the world as a stage where events happen. The stage is space-time, and the actors are particles moving across it. Twistor theory proposes that the stage itself is not fundamental. Instead, it's constructed from the relationships between the actors. A twistor is not a particle in space-time. It's a more abstract mathematical object that describes not just a particle, but its energy and its spin, its inherent angular momentum. Most importantly, a twister is defined by where it's going, its light-like trajectory. In this framework, a point in our familiar four-dimensional spacetime is not a primary ingredient. Instead, a point is defined by all the twisters that pass through it. The stage is built from the paths of the actors. This perspective reversal offers a breathtakingly elegant way to tackle the problem of quantum gravity. In our standard approach, the smooth, continuous fabric of spacetime in general relativity clashes violently with the fuzzy, probabilistic nature of quantum mechanics. But if spacetime is not fundamental, then this conflict might simply vanish. The notorious singularities inside black holes, where general relativity predicts spacetime curvature becomes infinite, might be artifacts of our flawed point-based view. In the twister picture, these infinities could be naturally smoothed out because the underlying twister geometry doesn't break down in the same way. It's a completely fresh starting point that bypasses the traditional roadblocks. Where twister theory has already proven its extraordinary power is in the seemingly unrelated field of calculating scattering amplitudes. These are the probabilities for particles to collide and transform into other particles in high-energy experiments. For decades, calculating these amplitudes for more than a few particles involved nightmarishly complex integrals with thousands of terms that would cancel each other out in mysterious ways. It was algebraically messy and deeply inefficient. Then, a revolution began. Researchers using twister-inspired methods discovered that they could replace these monstrous calculations with astonishingly simple and beautiful geometric drawings. They found that the incredibly complex probability for, say, two gluons to scatter off each other and produce multiple other gluons could be represented by a polygon. Each corner of the polygon corresponds to a particle, and the area of the polygon gives you the amplitude. The hidden symmetries of the theory, which were completely obscured in the traditional calculus, become visually obvious in this twister space. Calculations that once took weeks and filled reams of paper could now be done in minutes, sometimes even by hand. This wasn't just a new method. It was a revelation that the universe was using a geometric language far more compact and elegant than we had ever imagined. The twisters were revealing a hidden simplicity beneath the apparent complexity of particle interactions. While twister theory remains a work in progress for a full description of quantum gravity, its successes are impossible to ignore. It stands as a powerful testament to the power of a truly novel perspective. Sometimes the key to solving a profound mystery isn't to push harder down the same path, but to step back and ask if we're even looking at the problem the right way. Twister theory asks us to consider that the universe is not built from tiny dots in a void, but from a web of relationships and directions, a cosmic network where the threads are more real than the knots they form. This brings us to one of the most profound debates in the history of science, a question that cuts to the very heart of reality. Is the universe fundamentally random, or does it just appear that way? For decades, the bizarre and counterintuitive rules of quantum mechanics have suggested that at the smallest scales, nature is governed by pure chance. But what if this randomness is merely a veil hiding a deeper, deterministic order? This is the promise of hidden variable theories, which propose that particles have definite properties all along, guided by unseen forces that restore a beautiful causal symmetry to the quantum world. The most famous of these is the de Broglie-Bohm pilot wave theory, an idea that began with Louis de Broglie in the 1920s and was fully developed by David Bohm in the 1950s. This theory offers a breathtakingly elegant alternative to the standard probabilistic interpretation. It suggests that particles, like electrons, are not ethereal probability clouds until measured. Instead, they are real, point-like objects with perfectly well-defined positions and trajectories at all times. So, what guides them on their path? A mysterious pilot wave, an invisible field that permeates all of space and literally pushes the particle around. The particle is like a surfer being carried by a wave, its path completely determined by the shape of this guiding wave. this creates a stunning form of non-local symmetry. The pilot wave connects every particle in the universe instantaneously. If you change the conditions for one particle, the information ripples through the pilot wave faster than light, affecting all other particles entangled with it. This sounds like it violates Einstein's theory of relativity, which forbids faster than light communication. And indeed, Einstein famously called this kind of instant connection spooky action at a distance. But here's the crucial point: while the information travels faster than light, it cannot be used to send a signal or a message. The theory is meticulously crafted to be completely consistent with all the empirical predictions of quantum mechanics. It just provides a different, more intuitive story behind the equations. For a long time, this was considered a philosophical preference, a matter of taste. How could you possibly test if reality is truly random or secretly deterministic? This is where the brilliant physicist John Stuart Bell entered the stage. In the 1960s, he devised a way to settle the argument once and for all. He derived a mathematical inequality, now known as Bell's inequality, that provides a clear test. If the universe is truly local and real, meaning objects have definite properties independent of measurement and no influence can travel faster than light, then any experiment must obey this inequality. But if quantum mechanics is correct and particles are truly connected in a spooky, non-local way, then Bell's inequality will be violated. The experiments, most famously those by Alain Aspect and his team in the 1980s, were decisive. They entangled particles like photons and measured their properties at distances that ensured no light-speed signal could possibly coordinate their behavior. Time and again, the results violated Bell's inequality. The universe had chosen sides. It demonstrated that no local hidden variable theory, one where influences travel at or below the speed of light, could ever explain the correlations we see. The world is genuinely non-local. Either particles communicate instantaneously or they don't have independent existence until measured. This was a monumental result, seemingly sounding the death knell for deterministic theories like pilot wave. But the story isn't quite over. The de Broglie-Bohm theory is a non-local hidden variable theory. It never claimed to be local. In fact, its entire mechanism relies on that instantaneous connection through the pilot wave. Therefore, it fully expects Bell's inequality to be violated and is completely consistent with the experimental results. It survives not as a local explanation, but as a deterministic one. It tells us that the universe might still be deterministic at its core, but that this determinism is woven together with a profound, faster-than-light connectedness that makes the entire cosmos a single, inseparable whole. The implications of this are staggering. It suggests a cosmos where everything is intimately and instantly connected, a hidden symmetry of influence that binds every particle to every other. We don't perceive this directly in our macroscopic world, much like we don't feel the Earth hurtling through space, but it could be the fundamental architecture of reality. The choice between the standard quantum view and the pilot wave view then becomes less about experimental proof and more about philosophical preference. Do you prefer a universe of inherent randomness or one of determined but deeply connected motion? Both describe the same outcomes, but they paint two vastly different pictures of the underlying cosmic machinery. Yet throughout this dizzying exploration of non-locality and hidden variables, the ghost of Einstein's greatest triumph, general relativity, still haunts the edges of our understanding. Its equations predict their own downfall in the form of singularities, points of infinite density where the laws of physics simply break down. This mathematical meltdown is not just a theoretical curiosity. It represents a profound threat to the very predictability and order we expect from the cosmos. To rescue this cosmic order, we turn to a powerful and elegant conjecture proposed by Roger Penrose, an idea meant to shield the universe from its own worst excesses, the cosmic censorship hypothesis. Picture the equations of general relativity as a flawless map of reality. This map guides us beautifully through the warps and curves of spacetime, from the gentle pull of a planet's gravity to the mind-bending orbits around a black hole. But when we follow this map to its most extreme destination, the very center of a black hole, it leads us to a place called a singularity. Here, the map tells us that density becomes infinite, space-time curvature becomes infinite, and our reliable equations dissolve into meaningless gibberish. It's as if the map has a region labeled, "Here be dragons," a point where the rules of navigation themselves cease to exist. A naked singularity would be a catastrophe for physics. It would be a point of infinite curvature open to the wider universe, a place where anything could emerge and anything could happen, completely ungoverned by any known law of cause and effect. The predictability that is the bedrock of science would vanish. You could, in principle, throw something into a naked singularity and have a past paradox or a completely new universe fly back out. It would be a portal to utter lawlessness, rendering the future fundamentally unknowable. Penrose's cosmic censorship hypothesis is a bold and elegant solution to this terrifying prospect. In its simplest form, it is a conjecture that nature abhors a naked singularity. It proposes a fundamental rule of cosmic modesty, that every singularity must always be hidden from view, forever clothed by an event horizon. This horizon acts as a one-way membrane, a point of no return that not only traps matter and light, but also acts as an impenetrable curtain, shielding the rest of the universe from the unmitigated chaos at the black hole's heart. The event horizon, in this view, is not just a physical boundary, it is a guardian of cosmic order, preserving the sanctity of cause and effect throughout the observable universe. This hypothesis is powerful because it restores a profound symmetry to the cosmos, the symmetry of predictability. It ensures that from our perspective, outside any black hole, the laws of physics remain intact and reliable. We can still calculate the future evolution of spacetime based on initial conditions, confident that no unpredictable influence will burst forth from a naked singularity to ruin our calculations. The universe remains a comprehensible, orderly place, even if it contains regions of unimaginable violence, so long as those regions remain discreetly hidden from view. The quest to prove or disprove cosmic censorship has become a central drama in theoretical physics. Researchers have spent decades trying to break it to find a set of realistic conditions, be it through the collapse of exotic matter or the merger of spinning black holes, that could lead to a singularity tearing free of its horizon and becoming naked. While some mathematical models have suggested it might be possible, these scenarios often rely on perfectly symmetric, unrealistic starting conditions that are unlikely to occur in our messy, real universe. To date, no robust, physically plausible counterexample has been found, lending strong support to Penrose's original conjecture. It seems the universe may indeed have a deep-seated preference for order over lawlessness, using the event horizon as its ultimate instrument of cosmic censorship. But if the event horizon acts as a cosmic censor, guarding the predictable laws of physics we hold dear, then there exists another, far subtler particle that has been quietly breaking the rules right under our noses for decades. This brings us to the ghostly neutrino and one of the most startling discoveries of the last quarter century, a phenomenon that shattered a long-held symmetry and opened a new window into the universe's deepest workings, neutrino oscillations. For the longest time, the standard model of particle physics painted a beautifully symmetric picture of the lepton family. It consisted of three charged particles, the electron, muon, and tau, and their three neutral, ghost-like partners, the electron neutrino, muon neutrino, and tau neutrino. The symmetry was perfect and absolute. The model assumed quite sensibly that, like the photon, these neutrinos were completely massless. They were meant to be mere placeholders, zipping through the cosmos at the speed of light, forever unchanged, never interacting with anything. This was the lepton symmetry we thought we understood. Then, in the late 1990s, a massive detector buried deep in a Japanese zinc mine called Supersymmetry and delivered a bombshell. Scientists were studying neutrinos produced in the atmosphere by cosmic rays. They expected to detect equal numbers of muon neutrinos coming down from the sky above and coming up through the Earth from the atmosphere below. But the data revealed a shocking deficit. The neutrinos that had traveled a longer distance, those coming up through the planet, had mysteriously disappeared. The only plausible explanation was that they hadn't vanished at all. They had changed identities. The muon neutrinos were transforming into tau neutrinos during their journey, a process we now call neutrino oscillation. This single observation shattered the foundations of the old lepton symmetry. For a neutrino to oscillate, to morph from one flavor into another as it travels, it must violate two of the original model's sacred assumptions. First, neutrinos cannot be massless. The entire mechanism of oscillation relies on the different neutrino mass states having slightly different energies. And second, the flavors of neutrinos we detect, electron, muon, tau, cannot be the same as their mass states. They are instead a quantum mixture, a superposition. This means a neutrino produced as an electron neutrino is actually a blend of three different masses, and as it travels, these mass components evolve at different rates, causing the blend to change, sometimes appearing as a muon neutrino to a detector. The mathematical key that describes this mixing is known as the Pontecorvo-Maki-Nakagawa-Sakata matrix, or the PMNS matrix. Think of it as a recipe book or a rotation matrix. It precisely tells us how much of each mass state is in each flavor state. Just as the CKM matrix describes quark mixing, the PMNS matrix does the same for leptons, but with even larger mixing angles, indicating that neutrino mixing is far more pronounced and dramatic than anything we see in the quark sector. This matrix is now a fundamental part of our understanding of the universe, a required addition to the Standard Model's blueprint. The implications of this broken symmetry are monumental and point toward physics beyond our current understanding. The fact that neutrinos have mass, however tiny, is a direct clue that the Standard Model is incomplete. It doesn't predict these masses. Their origin remains one of the greatest open questions, potentially tied to grand unification or involving sterile neutrinos that could be dark matter candidates. Furthermore, this mixing opens the door to a potential gold mine, the search for CP violation in the lepton sector. Just as CP violation among quarks helped explain the matter-antimatter asymmetry, a similar effect with neutrinos could be the final, decisive piece of the puzzle. If neutrinos and antineutrinos oscillate at different rates, it would create a universal bias that could have tipped the scales in the early universe, favoring the creation of matter over antimatter on a cosmic scale. Experiments around the world are now racing to measure this effect, hunting for the subtle differences that could explain why we exist at all. The humble neutrino, once thought to be a mere spectral footnote, has become a central character in our quest to understand the universe's hidden symmetries and the profound ways in which they break. While the neutrino reveals a dramatic breaking of symmetry in the weak force, there exists another fundamental interaction where the absence of a break is just as baffling. This is the strong CP problem, a mystery so deep that its solution might point to an entirely new particle that could also make up the dark matter bathing our galaxy. To understand it, we need to look at the force that holds atomic nuclei together, the strong nuclear force. The mathematics of the strong force, encapsulated in a framework called quantum chromodynamics, naturally allows for a certain kind of violation of CP symmetry. This would mean that the force should treat particles and antiparticles differently in a mirrored world, much like the weak force does. The equations include a parameter whimsically called theta that controls the size of this effect. If theta were a significant number, even just a value of 1, it would lead to truly bizarre consequences. For instance, the neutron, a key component of every atom, would possess a large electric dipole moment. It would be ever so slightly lopsided, with a bit more positive charge on one end and negative on the other. This may sound minor, but it would be enough to throw the delicate balance of atomic physics into chaos, potentially preventing the formation of the complex atoms necessary for life as we know it. Yet when physicists measure the neutron with incredible precision, they find its electric dipole moment is vanishingly small, indistinguishable from zero. Theta is less than 1/1000th of a billionth. The question is not just why it's small, but why it is zero at all. Why does the strong force, which has every right to be CP violating, perfectly respect this symmetry? This fine-tuning seems unnatural, a cosmic coincidence that makes physicists deeply uncomfortable. It appears as if a dial in nature that could have been set to almost any value was instead carefully cranked all the way down to zero. This is the strong CP problem. In the 1970s, Roberto Pexi and Helen Quinn offered a breathtakingly elegant solution. They proposed that this theta parameter is not a fixed fundamental constant, but actually a dynamical field that can change its value across space and time. Their mechanism suggested that the universe naturally wants to settle into the state where theta is zero, because that is the lowest energy configuration, just like a ball rolling to the very bottom of a valley. This elegant idea not only solved the fine-tuning problem, but also predicted a remarkable side effect. A new, very light particle would be the quantum manifestation of this field. This particle was named the Action after a brand of laundry detergent because it was proposed to clean up the strong CP problem. The properties of this hypothetical particle are what make it so extraordinarily compelling. It would be electrically neutral, incredibly light, potentially billions of times lighter than an electron, and would interact with matter only very weakly, slipping through entire planets as if they weren't even there. These are not just convenient traits, they are the exact characteristics astronomers attribute to cold dark matter. In one stroke, the Action provides an elegant solution to a deep puzzle in particle physics and a prime candidate for the mysterious substance that makes up most of the matter in the cosmos. Vast halos of these particles could be gravitationally binding galaxies together right now, a ubiquitous but invisible presence born from the universe's desire for symmetrical perfection. The hunt for the Action is one of the most creative and delicate experiments in modern science. Because they interact so feebly, they cannot be found with traditional particle colliders. Instead, physicists have built extremely sensitive detectors that are more like exquisite radios tuned to a specific, unknown station. The most prominent approach is to use a powerful magnet inside a supercooled cavity. The theory suggests that in the presence of a strong magnetic field, an Action could very rarely convert into a microwave photon. By meticulously tuning the resonant cavity and listening for a faint, unexpected microwave signal against the background noise of the universe, experiments like the Action dark matter experiment hope to hear the whisper of actions converting within their detector. It's a painstaking search for a needle in a cosmic haystack, but the potential reward nothing less than the identity of dark matter and the resolution of a foundational mystery makes it one of the most thrilling quests in physics today. Yet if a particle as ghostly as the Action could be born from a need for symmetry, what happens if we question the very stage on which all particles perform, the smooth, continuous fabric of spacetime itself? Our next theory proposes a radical rewriting of the cosmic rulebook, suggesting that at the very smallest scales, the universe operates not like a fluid film, but more like a finely woven mesh where the very order of events matters. This is non-commutative geometry, a framework that dares to imagine a world where the coordinates of space and time no longer follow the commutative rules we take for granted. In our everyday algebra, we learn that 3 times 4 gives the exact same result as 4 times 3. The order of the operation doesn't matter, the numbers commute. We assume the same is true for the coordinates of spacetime. Measuring an object's position first in the x direction and then in the y should be identical to measuring y first and then x. The universe, in our classical view, doesn't care about the sequence. But what if this fundamental commutativity breaks down at the Planck scale, at distances so tiny they approach the fundamental grain of reality? Non-commutative geometry proposes exactly that. In this view, trying to pinpoint a location in spacetime with infinite precision becomes a meaningless endeavor. The very concepts of here and now develop a fundamental fuzziness, suggesting that space itself is composed of indivisible, discrete units. This idea finds a powerful analogy in the birth of quantum mechanics itself. When Heisenberg discovered his famous uncertainty principle, he did so by considering the mathematics of matrices, where the order of multiplication absolutely matters. In his formalism, the matrix representing a particle's position multiplied by the matrix for its momentum does not equal the momentum matrix multiplied by the position matrix. This non-commutativity is the mathematical heart of quantum uncertainty. It's why you cannot know both a particle's position and its momentum with perfect accuracy. Non-commutative geometry applies this same profound insight directly to the fabric of spacetime. It suggests that the coordinates of space themselves behave like quantum operators that do not commute. The result is a natural and inherent blurriness to the structure of the universe at its smallest scales, a fundamental pixelation that prevents the formation of the nasty singularities that plague classical general relativity. One of the most captivating consequences of this approach is a direct challenge to the notion of a singular Big Bang. In several models built on non-commutative principles, the overwhelming density and curvature that we traditionally associate with the beginning of time are naturally smoothed out. The universe does not erupt from a point of infinite density, but rather emerges from a prior collapsing phase, bouncing into our expanding cosmos thanks to the repulsive gravitational effects generated by the spacetime non-commutativity. This provides a compelling and elegant alternative to the traditional inflationary paradigm, one that naturally avoids the initial singularity and offers a bridge to a potentially cyclical history of the cosmos. Beyond cosmology, this geometry also suggests subtle but testable modifications to the behavior of matter in extreme environments. For instance, the dispersion of light traveling across the vast distances of the universe could be minutely altered if spacetime has this granular, non-commutative structure. Very high energy gamma rays from distant cosmic explosions could arrive at our telescopes at slightly different times than lower energy photons, not because they were emitted at different moments, but because their ultra-high frequencies cause them to probe the fine-grained structure of spacetime itself, interacting with its discrete geometry in a way that affects their speed. While no such effect has been definitively confirmed, it represents a thrilling possibility that we could one day detect the grain of spacetime by reading the messages carried by the most energetic light in the universe. Imagine trying to understand the smooth, curved surface of a pond by looking at it through a fine mesh screen. You'd see countless tiny facets, a geometric approximation of the water's surface. Now apply that idea to the very fabric of spacetime itself. This is the essence of a radically different approach to quantum gravity known as causal dynamical triangulation. It's a theory that builds the entire universe from the ground up, piece by tiny geometric piece, and in the process reveals how our familiar four-dimensional reality might miraculously emerge from a set of very simple rules. The core idea is both powerful and straightforward. Instead of thinking of spacetime as an infinitely smooth, continuous fabric, imagine it is constructed from an enormous number of tiny, fundamental building blocks. In this approach, those blocks are simple, triangular pieces of geometry called simplices. In 2 dimensions, a simplex is a triangle. In 3 dimensions, it's a tetrahedron. And for our 4-dimensional spacetime, theorists use a 4-simplex, a complex shape that generalizes the tetrahedron into a higher dimension. The entire cosmos is envisioned as a massive, shimmering network of these geometric atoms, all glued together along their faces. It's a cosmic mosaic, a pixelated version of reality at the tiniest possible scale. But there's a crucial, defining constraint in its name: causal. This is the master rule that brings order to the construction. In this framework, time is not just another dimension like space. It is treated as fundamentally special. Each tiny simplex is arranged so that cause always precedes effect. You can't have a configuration where a future event influences something in the past. This causal structure acts like the grain in a piece of wood, guiding how the pieces can be assembled and preventing the chaotic, nonsensical jumbles that can appear in other similar approaches. It ensures the entire construction respects the most sacred rule of physics, that every event has a cause that came before it. Now, the true magic happens when you let this universe evolve on a computer. Physicists run massive simulations, essentially telling the computer to assemble trillions upon trillions of these geometric pieces in every possible random way, but always strictly obeying the causal rule. They then apply the principles of quantum mechanics to sum over all these possible histories, a technique famously used by Richard Feynman. They aren't programming in four-dimensional spacetime. They are feeding the computer the most basic ingredients, the geometric atoms and the causal glue, and then asking it what large-scale structure naturally arises from this chaotic quantum soup. The results are nothing short of astonishing. When these simulations run, something beautiful and profound happens. Out of the random, jumbled network of triangles and tetrahedrons, a clear, stable, and extended structure spontaneously forms. The geometry dynamically organizes itself, and from the simple, piecewise flat building blocks, a smooth, curved four-dimensional spacetime emerges all on its own. It's like watching a crystal form from a turbulent solution. The symmetry and order were hidden in the rules all along, just waiting to reveal themselves on a large scale. This emergence of four dimensions is a monumental success, as many other quantum gravity theories struggle to explain why our universe has precisely three spatial dimensions and one time dimension, instead of some other number. Furthermore, this emergent spacetime exhibits behavior that looks tantalizingly familiar. On large scales, it behaves according to the equations of Einstein's general relativity, seamlessly reproducing the curved geometry that governs planets, stars, and galaxies. But the model also makes a stunning prediction for the ultra-small scale. It suggests that the effective dimensionality of the universe might actually change as you zoom in. While our everyday experience is firmly four-dimensional, the theory predicts that at the very tiniest distances near the Planck scale, the universe might become two-dimensional. This fractal-like property could provide a natural cutoff that prevents the infinities that have plagued quantum gravity for decades, offering a potential path to finally unifying the physics of the very large with the very small. Yet as we marvel at the idea of spacetime emerging from a sea of geometric possibilities, we must also ask a more fundamental question: how does anything in the quantum realm ever decide to happen at all? This brings us to a theory that is as profound in its simplicity as it is radical in its implications, a revolutionary way of thinking about reality pioneered by the legendary physicist and storyteller Richard Feynman. This is the path integral formulation, an approach that doesn't just calculate probabilities but suggests that a particle, in a very real sense, takes every possible path to its destination simultaneously, weaving history from a symmetric sum of all possible stories. To appreciate the sheer brilliance of this idea, we first have to understand the problem it solved. The traditional way of doing quantum mechanics, with its waves and matrices, worked well but often felt like a collection of complex mathematical rules without a clear, intuitive picture. Feynman, with his unique genius for seeing things differently, asked a deceptively simple question: how does a particle actually get from point A to point B? The answer he devised was as shocking as it was beautiful. He proposed that we shouldn't imagine the particle taking a single, definite path, like a little baseball arcing through the air. Instead, we must consider that it somehow explores every single conceivable route between those 2 points. It goes in straight lines, it loops the loop, it takes a detour to the Andromeda Galaxy, and back. Every possible trajectory is on the table. The mathematical heart of this idea is the path integral itself. Feynman's method involves assigning a number, a kind of quantum influence, to every one of these infinity of paths. This number is a complex phase, which you can think of as a tiny arrow spinning at a certain speed and pointing in a specific direction. To find out the probability that the particle will actually be detected at point B, you perform a breathtakingly ambitious calculation. You sum up or integrate the contributions from every single one of these paths. The arrows from all these different histories add together like waves in a pond. For most paths, the arrows point in random directions and cancel each other out, leaving no net effect. But for paths very close to the classical trajectory predicted by Newton, the arrows line up and reinforce each other, creating a strong signal. This is why we see particles behaving almost classically in our everyday world, not because they follow one path, but because the contributions from the paths near that trajectory constructively interfere. This is where we see a breathtaking and fundamental symmetry at play. In Feynman's formulation, every possible history is treated with perfect democratic equality. The path where an electron behaves itself and the path where it acts completely erratically are given the same initial weight in the calculation. There is no preferred path. The symmetry among all histories is absolute. The universe, in this view, does not discriminate. It is only through the subsequent summation, the intricate interference of all these phases, that a particular outcome is selected. This symmetric treatment of all possibilities is the cornerstone of the method's immense power and elegance. The true magic of the path integral, however, is how it effortlessly bridges the quantum and classical worlds. When we apply this formalism to objects much larger than particles, the results are extraordinary. For something like a baseball, the number of possible paths is still infinite, but the phase associated with each path oscillates wildly. The only paths that don't cancel themselves out are those in a very small region where the phase is stable, and that region is exactly the single, smooth trajectory described by classical mechanics. Feynman's sum over histories seamlessly explains why big things appear to obey Newton's laws, while tiny things do not. It's not that the baseball isn't exploring every path. It's that all paths except the classical one interfere destructively and are thus effectively invisible. But Feynman's ambition didn't stop with single particles. His formulation provided the most natural and powerful language for modern quantum field theory, the framework that describes everything from electrons to Higgs bosons. In quantum field theory, we're not summing over paths of particles anymore. We're summing over all possible configurations of fields throughout all of spacetime. This is an even more vast and mind-boggling concept. The path integral becomes a tool for calculating the probability of any event by considering every possible way the fields could have fluctuated and interacted to bring that event about. It is the ultimate expression of the sum over histories idea, and it is absolutely indispensable for making the precise calculations that match our most sophisticated particle accelerator experiments. Perhaps the most poetic aspect of Feynman's framework is the beautiful diagrams that bear his name. These are not literal pictures of particle paths, but powerful graphical tools that emerge directly from the path integral mathematics. Each diagram represents one specific way that the fields could have interacted one history out of the infinite sum. Drawing all possible diagrams for a given particle collision and adding their contributions is exactly how physicists use the path integral to compute probabilities. These squiggly lines and loops are more than just calculational shortcuts. They are a visual representation of the universe's deepest democratic principle, a testament to the idea that reality is built from the symmetric consideration of every story that could possibly be told. But if the path integral shows us how reality is woven from countless possibilities, then spontaneous symmetry breaking is the mechanism that explains why the universe we actually experience seems to have chosen just one. This is one of the most profound and beautiful ideas in all of physics, a concept that reveals how a perfectly symmetric set of laws can inevitably lead to a world that appears starkly asymmetric. It's the process by which the universe's true, hidden symmetry becomes disguised, forcing the world to make a choice and, in doing so, giving rise to everything from the mass of particles to the very structure of matter itself. To understand this, imagine a perfectly sharp pencil balanced on its tip. The situation is exquisitely symmetric. From a bird's eye view, every direction around the pencil looks exactly the same. The laws of physics governing the pencil don't prefer north over south or east over west. This is the state of perfect, unbroken symmetry, but we all know this state is unstable. The slightest breath of air, the tiniest vibration, will cause the pencil to fall, and when it does, it must choose a single direction in which to lie down. In that moment, the perfect rotational symmetry of the balanced pencil is broken. The universe didn't change the laws of physics, the laws were always symmetric. But the outcome, the final resting state of the pencil, is now undeniably asymmetric. The symmetry is still there in the rules of the game, but it's hidden from view in the result. This is the essence of spontaneous symmetry breaking. Now, let's take this simple idea and apply it to the quantum realm, where it becomes the engine of reality. The most famous example is the Higgs mechanism. Picture not a pencil, but a field that permeates all of space, known as the Higgs field. In the extreme energies of the early universe, this field sat at a symmetric point where its value was zero. Much like the balanced pencil, this was a state of high energy and instability. As the universe expanded and cooled, it was as if the Higgs field rolled down into a stable state, but this stable state required it to take on a non-zero value everywhere. The field had to choose a value, and in doing so, it broke the symmetry of the electroweak force. This single event is what differentiates the electromagnetic force carried by the massless photon from the weak nuclear force carried by the massive W and Z bosons. The bosons associated with the broken symmetry directions feel the Higgs field as a sort of quantum drag, acquiring mass, while the photon, corresponding to the remaining unbroken symmetry, zooms through untouched. This isn't just a theory, it's the mechanism confirmed by the discovery of the Higgs boson at the Large Hadron Collider, the quantum excitation of this all-important field that broke the world's symmetry and made our material universe possible. But the influence of this mechanism doesn't stop there. It operates just as powerfully in the realm of the strong nuclear force, the glue that holds atomic nuclei together, through a process known as chiral symmetry breaking. In the world of quantum chromodynamics, if the quarks that make up protons and neutrons were massless, the theory would possess a beautiful symmetry between left-handed and right-handed particles. Yet, we don't live in that world. Protons and neutrons have a significant mass, nearly all of which does not come from the Higgs mechanism, but from the dynamics of the strong force itself. This is where spontaneous symmetry breaking works its magic again. The vacuum of empty space becomes a kind of medium, a condensate of quark-antiquark pairs that fills the universe. This condensate is not symmetric. It picks a preferred direction, much like the fallen pencil. This breaking of chiral symmetry gives rise to the overwhelming majority of the mass of the protons and neutrons that constitute the atoms in our bodies and everything we see around us. It also explains the existence of the pion, a light particle that acts as the force carrier of the nuclear force and is understood to be the Nambu-Goldstone boson, the almost massless ripple that always appears when a continuous symmetry is spontaneously broken, a whisper of the perfect symmetry that was lost. This process is not confined to the esoteric world of particle physics. It is the universal language of phase transitions. When water freezes into ice, the liquid state possesses full translational and rotational symmetry. Every point and every direction is equivalent. But when ice crystals form, the water molecules spontaneously arrange themselves into a rigid, repeating lattice. They choose specific orientations, locking into a fixed structure that breaks the continuous symmetry of the liquid. The resulting crystal is manifestly asymmetric, yet the underlying laws of electromagnetism and quantum mechanics that govern the water molecules are still perfectly symmetric. We see this pattern everywhere, in the alignment of magnetic domains in a piece of iron, in the emergence of superconductivity where electrons pair up and break electromagnetic symmetry, and even in biology where the choice of left-handed amino acids and right-handed sugars in all life on Earth might be the result of a spontaneous symmetry-breaking event in our planet's primordial soup. It is a fundamental principle that orchestrates order from chaos, guiding the universe to make specific choices that create the rich, complex, and asymmetric reality we call home. Now consider a connection so strange it seems pulled from the pages of science fiction, where two of the most baffling ideas in physics turn out to be two sides of the same coin. This is the ER equals EPR conjecture, a breathtaking proposal that dares to link the spooky, instantaneous bond of quantum entanglement with the fantastical, space-bending tunnels of wormholes. At its heart, this idea suggests a profound and hidden symmetry, that the fabric of space-time and the quantum connections that weave through it are not separate things but deeply, fundamentally intertwined. To understand this radical proposal, we need to look at its two halves. First, ER. This stands for Einstein and Nathan Rosen, who back in 1935 explored the possibility of a bridge connecting two distant points in spacetime, what we now commonly call a wormhole or an Einstein-Rosen bridge. In the equations of general relativity, these structures are possible, but they are notoriously unstable. They would snap shut in an instant, preventing anything, even light, from passing through. Then, in that very same year, we have EPR, which stands for Einstein, Podolsky, and Rosen. In a famous paper meant to highlight the absurdity of quantum mechanics, they described the phenomenon we now call quantum entanglement. They pointed out that two particles could become linked in such a way that measuring the property of one would instantly determine the property of the other, no matter how far apart they were separated, an effect Einstein famously derided as spooky action at a distance. For decades, these two 1935 ideas, wormholes and entanglement, were thought to be completely unrelated. One was a curious feature of the geometry of space-time, the other was a bizarre feature of the quantum world. But in 2013, physicists Juan Maldacena and Leonard Susskind put forth a conjecture that was as simple as it was revolutionary: ER equals EPR. They proposed that these two concepts are actually equivalent. An Einstein-Rosen bridge is the same thing as a pair of entangled particles. In other words, what we perceive as spooky action at a distance is not some invisible, instantaneous signal flying between particles. Instead, it is a physical connection, a microscopic Planck-scale wormhole that geometrically links them. The particles aren't communicating, they are literally sharing a tiny quantum piece of the same space-time fabric. This idea provides a stunningly elegant geometric picture for entanglement. Imagine two entangled electrons. According to this conjecture, if you could somehow zoom into the Planck scale, you wouldn't see two separate particles. You would see a single, ultra-small wormhole, a gravitational tendril connecting them. Their seemingly magical correlation is simply a consequence of this short physical bridge. This immediately demystifies the spookiness. There's no faster-than-light communication because the two particles are not truly separate entities. They are two mouths of the same geometric structure. The connection was always there, woven into the geometry of the universe itself. The implications of this for the black hole information paradox are nothing short of transformative. Recall the problem. Information that falls into a black hole seems to be lost forever when the black hole evaporates, violating quantum mechanics. But if ER equals EPR is correct, then the solution becomes beautifully geometric. The pairs of particles that are spontaneously created at the event horizon, one falling in and one flying out as Hawking radiation, are not just randomly correlated. They are entangled, and if they are entangled, then according to the conjecture, they must be connected by tiny wormholes. This web of microscopic bridges would stitch the interior of the black hole to the outgoing radiation, creating a pathway for information to escape. The information isn't burning up, it's traversing these quantum wormholes, being slowly and meticulously encoded onto the Hawking radiation. This provides a concrete, geometrical mechanism for how information is preserved, solving the paradox by uniting the laws of quantum mechanics with the geometry of general relativity. Perhaps the most profound consequence of this idea is the vision it offers for the unification of physics. For a century, we have struggled to reconcile the smooth, continuous geometry of Einstein's gravity with the fuzzy, probabilistic nature of quantum mechanics. The ER equals EPR conjecture suggests that this divide is an illusion. It posits that spacetime itself is not a fundamental stage but an emergent property that arises from a vast cosmic network of quantum entanglement. Think of an incredibly complex tapestry. From a distance, it looks like a smooth, continuous image, but up close, you see it is actually woven from countless individual threads. In this view, the smooth geometry of spacetime is the image we see from afar, while the threads are the entanglements between quantum particles. The very fabric of space and time may be knit together by these quantum connections. This leads to a truly radical and testable prediction. If spacetime is built from entanglement, then disturbing that quantum entanglement should have a direct effect on geometry. In principle, if you could somehow take two entangled particles and carefully disentangle them, you would not just be breaking a quantum link. According to this idea, you would be severing the microscopic wormhole that connects them, effectively causing a rupture in the spacetime between them. While performing such an experiment on a pair of particles is far beyond our current technology, this conceptual framework gives physicists a new language and a new set of tools to explore the quantum nature of gravity. It transforms the black hole information paradox from a confusing quantum puzzle into a tractable question about the geometry of spacetime. The ER equals EPR conjecture is more than just a clever idea. It is a potential roadmap pointing toward a deeper layer of reality where the language of quantum information and the language of geometry are finally and perfectly unified. Now, if the mysteries of quantum gravity and holographic universes seem almost too vast to comprehend, it's worth remembering that some of the most profound symmetries in nature are not just hidden in the cosmos, but can be found right here on Earth, in the seemingly mundane behavior of materials all around us. This brings us to a stunningly powerful idea, that the same conformal symmetry which might govern the infinite cycles of the universe also emerges with perfect precision in the physics of a simple magnet cooling on a lab bench. Picture an ordinary iron magnet. When it's hot, its atomic magnets are in chaos, pointing in every which direction. But as it cools to a very specific, critical temperature, something magical happens. The system can't decide whether to be disordered or ordered. It hovers perfectly on the knife's edge between the two, and in that moment of profound indecision, it becomes scale invariant. Fluctuations in the magnetic field appear at every possible size, from the distance between a single pair of atoms all the way up to the size of the entire magnet itself. Zoom in on any part of it, and you'll see the same intricate, self-similar pattern repeating. This critical point is where the magnet loses all sense of scale, and in doing so, gains a powerful new symmetry, conformal invariance. This is far more than a curious observation. It is a computational superpower. Conformal symmetry is so restrictive that it can completely determine the outcome of a physical system. For a condensed matter physicist studying a material at its critical point, this symmetry is like a master key. It allows them to calculate exact answers for properties that would otherwise be impossible to solve with traditional methods. They can determine precise numbers for how the magnetism decays with distance or how the heat capacity diverges at the critical temperature. These aren't approximations, they are exact results derived purely from the incredible constraints imposed by the conformal symmetry. The universe in these fleeting moments becomes mathematically transparent. The tool that makes this possible is known as the conformal bootstrap. Imagine you're trying to deduce the rules of a game just by watching it be played. The conformal bootstrap is a strategy that says, if the game is conformally symmetric, then it must be self-consistent. The moves players make at one scale must agree perfectly with the moves they make at every other scale. By demanding this immense self-consistency, physicists can set up a system of equations that often has only one possible solution. It's a way of pulling yourself up by your own bootstraps, using the symmetry alone to define the entire game. This method has been wildly successful, providing some of the most accurate theoretical predictions ever made in condensed matter physics. But the connections run even deeper, creating a breathtaking bridge between the world of tabletop experiments and the most abstract theories of quantum gravity. Recall the AD/CFT correspondence, which posits a duality between a gravitational theory in a warped anti-de Sitter space and a conformal field theory on its boundary. For years, this was a playground for string theorists working on problems like black holes. But then came a revolutionary realization. The critical systems studied by condensed matter physicists are conformal field theories. This means that a magnet at its critical point is described by the same mathematical language as a certain theory of quantum gravity in a higher dimensional universe. The exotic quantum fluctuations dancing through the magnet could be holographically dual to the warping of spacetime in a world with an extra dimension. This incredible link turns a block of iron into a potential analog for a black hole. Calculations about the entanglement of spins in the magnet can be translated into calculations about the geometry of a hypothetical gravitational universe and vice versa. It's a partnership that grants practical gifts to both fields. String theorists gain access to real-world, experimentally tunable systems to test their ideas, while condensed matter physicists receive a powerful new toolkit of holographic methods to tackle unsolvable problems in their own domain. This synergy is already yielding spectacular results. Researchers have used holographic techniques inspired by AD/CFT to model incredibly complex materials, such as high-temperature superconductors. The strange, fluid-like behavior of electrons in these materials, which is notoriously difficult to describe with standard quantum mechanics, finds a more natural home in the language of gravitational duals. A black hole's event horizon can be used to model the electrical resistance of a superconductor, turning a deeply quantum mystery into a problem of classical geometry. What began as a theoretical curiosity about magnets and phase transitions has blossomed into a full-fledged research program, suggesting that the codes to unlock the universe's greatest secrets might be hiding not only in the distant cosmos, but in the ordered patterns of materials we can hold in our hands. But just as the universe reveals one layer of hidden geometry, string theory unveils another that is perhaps even more counterintuitive, a symmetry that fundamentally challenges our classical notions of size and distance. This is T-duality, a remarkable property where the entire physical behavior of strings remains completely unchanged if you swap a large, expanded dimension for an unimaginably small, contracted one. Imagine a universe where a guitar string stretched across a vast concert hall could produce the exact same note as one strung on a miniature instrument the size of an atom. That is the strange and beautiful world T-duality opens up for us. To grasp this, we need to remember that strings are not point particles, they are extended, one-dimensional objects. This means they can do something particles cannot. They can wrap around a compact dimension. Picture a single dimension curled up into a circle. A point particle confined to this circle can only occupy specific locations like beads on a necklace. But a closed string has two distinct ways of existing in this space. First, it can simply vibrate as it moves along the circle, much like a particle would. These vibrations are called momentum modes because their energy is related to the wavelength of their vibration around the circle, and this wavelength must fit perfectly into the circumference, quantizing the possible energy levels. But the string has a second, purely stringy option. It can literally wrap itself around the circular dimension like a rubber band stretched around a can. These are called winding modes, and their energy is directly proportional to the number of times the string wraps around the circle and the circle's radius. A string wrapped once around a large circle is stretched more tautly and contains more energy than one wrapped around a very small circle. This winding energy is a feature that has no analog in the world of point particles. It is a unique signature of the string's extended nature. Now, here is where the magic happens. The total energy of a string living in this compactified space is the sum of the contributions from its momentum modes and its winding modes. The stunning discovery of T-duality is that this total energy is perfectly symmetric if you simultaneously swap the radius r of the circle with its inverse, 1 divided by r, and also exchange the momentum and winding numbers. In other words, the physics of a string theory on a circle of radius r is completely identical to the physics of the very same string theory on a circle of radius 1 divided by r. A large, roomy dimension and a tiny, cramped one are physically indistinguishable from the perspective of string vibrations. The implications of this are nothing short of mind-bending. It suggests there is a fundamental, minimal length in the universe, roughly the string length scale, beyond which the very concept of getting smaller loses its meaning. If you try to squeeze a dimension smaller than this length, T-duality tells us you don't get a more extreme smallness. You simply get a description of a large dimension all over again. The universe, in a sense, has a resolution limit, and attempting to probe beyond it just gives you a different view of the same physics. This provides a beautiful and elegant solution to the nasty problem of singularities that plague classical general relativity, as the geometry simply cannot collapse to a point of zero size. This duality also forces us to radically redefine what we mean by geometry. In Einstein's theory, the geometry of spacetime is a fixed classical background, the stage on which physics plays out. But T-duality reveals that in string theory, geometry is an emergent secondary property. There is no absolute, God-given notion of whether a dimension is big or small. It depends entirely on which dual description you are using to observe it. Two seemingly different geometric backgrounds can describe the exact same physical reality. This elevates symmetry to a position of supreme importance, suggesting that the true, fundamental description of the universe might be written in a language that is beyond geometry entirely, a formalism where concepts like size and distance are not primitive but derived. T-duality isn't just a curious trick, it is a profound clue that we must look beyond our classical intuition to find the universe's most basic operating principles. Yet if the fabric of spacetime emerges from a web of quantum entanglements and dualities, then the objects that warp this fabric most extremely, black holes, might also be far simpler and more symmetric than anything we've encountered before. This brings us to a pair of ideas that have utterly transformed our understanding of these cosmic monsters, revealing them not as complicated mazes of lost information, but as objects of stunning, almost minimalist elegance. This is the realm of black hole thermodynamics and the no-hair theorems, a domain where the terrifying complexity of gravitational collapse gives way to a description of beautiful and profound simplicity. Let's start with the no-hair theorem, a concept with a wonderfully evocative name. It proposes that when matter collapses to form a black hole, it undergoes a remarkable cosmic forgetting. All the intricate details of the material that fell in the complex structure of the star, its chemical composition, whether it was made of matter or antimatter, even the very identity of the particles themselves are completely erased. The resulting black hole can be described by just three, and only three, observable parameters: its mass, its electric charge, and its spin or angular momentum. Imagine taking a magnificent library containing every book ever written, burning it to ashes, and then being able to describe the entire result with just three numbers. That is the radical simplicity implied by this theorem. A black hole, according to this idea, has no hair, no distinguishing features or frizz beyond these three bare quantities. It doesn't matter if you form a black hole from a collapsed star or a perfectly sculpted sphere of pure hydrogen. If the final mass, charge, and spin are identical, they are utterly indistinguishable. This represents a staggering symmetry in nature, suggesting that the infinite variety of possible initial conditions all flow toward one of a surprisingly small number of final, identical states. But if black holes are so simple, how do we reconcile that with the second law of thermodynamics, which states that the total disorder or entropy of a closed system must always increase? Throwing a priceless Ming vase into a black hole seems to permanently decrease the universe's total entropy, violating this sacred law. This paradox led the physicist Jacob Bekenstein, guided by John Wheeler's insights, to a revolutionary proposal. He suggested that black holes must themselves have entropy, and a tremendous amount of it. This entropy is not hidden in the complex jumble of matter inside, but is instead profoundly encoded on the black hole's one-way surface, its event horizon. Bekenstein proposed that the entropy of a black hole is proportional to the surface area of its event horizon. The larger the black hole, the greater its area and the greater its entropy. This means that when the vase falls in, the increase in the black hole's entropy more than compensates for the loss of the vase's entropy, preserving the second law for the entire cosmos. This was a breathtaking connection, but it was Stephen Hawking who completed the puzzle and ignited an entire field. If a black hole has entropy, then by the fundamental laws of thermodynamics, it must also have a temperature. Anything with a temperature must radiate energy. Hawking's calculations showed that due to quantum effects near the event horizon, black holes are not perfectly black after all. They slowly emit a faint glow of radiation, now known as Hawking radiation, and in the process they gradually lose mass and evaporate. This discovery cemented the analogy between black holes and thermodynamics into a direct physical correspondence, leading to the formal laws of black hole mechanics. The first law draws a direct parallel to the conservation of energy. It states that any change in a black hole's mass is equivalent to a change in its energy, and this is related to changes in its surface area, entropy, and its other parameters like angular momentum and charge, much like how adding energy to a hot gas changes its internal energy and entropy. The second law, that the total area of all event horizons can never decrease, is the direct analog of the entropy law. The third law states that it is impossible to reduce a black hole's temperature to absolute zero by any finite process, which mirrors the third law of thermodynamics. And finally, the zeroth law establishes that the surface gravity of a stationary black hole is constant across its entire event horizon, just as the temperature is constant throughout a body in thermal equilibrium. This incredible correspondence is far more than a mere mathematical analogy. It is a powerful clue that thermodynamics is not just about the behavior of steam engines and gases, but is deeply woven into the very fabric of spacetime and gravity. It suggests that the fundamental laws of the universe might be, at their heart, informational and statistical. The immense entropy of a black hole points to an astronomical number of microscopic quantum states that are hidden from our view, all of which contribute to that single, simple macroscopic description of mass, charge, and spin. The no-hair theorem, then, isn't a statement about the absence of complexity, but about its incredible compression. The information is not lost. It is scrambled and stored on the horizon in a way that makes it virtually inaccessible, presenting to the outside world a facade of perfect, symmetric simplicity. This union of gravity, quantum mechanics, and thermodynamics is perhaps our strongest hint that we are nearing a unified understanding of reality, where the most violent objects in the cosmos obey the same serene statistical laws as a warming teapot. But what if the powerful principles of supersymmetry, this cosmic mirror between particles, could be scaled down and applied not to the entire universe, but to the very mathematical heart of quantum systems themselves? This brings us to a fascinating and deeply elegant application known as supersymmetric quantum mechanics. Here, we aren't hunting for new particles. Instead, we use the formal structure of supersymmetry as a brilliant mathematical toolkit, one that allows us to solve seemingly impossible quantum problems with astonishing clarity and gain profound insights into the hidden symmetries woven into the fabric of reality. To understand how this works, we need to shift our perspective. In high-energy physics, supersymmetry is about pairing fermions and bosons. In its quantum mechanical version, the core idea is reframed around the concept of partner potentials. Imagine you have a quantum system described by a specific potential energy landscape. Think of a valley that a particle is trapped in. The physics of this system is determined by its energy spectrum, the set of allowed energy levels that a particle can have, much like the specific rungs on a ladder. Supersymmetric quantum mechanics provides a method to generate a brand new partner potential. This isn't just any random new valley. It's a potential meticulously crafted to be the supersymmetric partner of the first. The magic is that the energy spectra of these two partner potentials are intimately related. With the exception of possibly the very ground state, the energy levels of these two systems are perfectly identical. For every excited state in the first potential, there is a corresponding excited state with the exact same energy in its partner. This relationship is governed by a powerful mathematical machinery built around supercharges. These are operators that act like a ladder, but instead of moving you up and down the energy levels of a single system, they map the states of one system directly onto the states of its partner. This interplay creates a beautiful structure where the two Hamiltonians, the mathematical objects that encode the total energy of each system, are essentially two sides of the same supersymmetric coin. This formalism isn't just theoretical elegance, it's a practical powerhouse for solving the Schrödinger equation exactly for certain complex potentials that would otherwise be completely intractable. The true power of this technique is revealed through a concept called shape invariance. If a potential and its supersymmetric partner share the same functional form and only differ by a simple change of parameters, say, a slight shift in depth or width, then they are said to be shape invariant. This is the holy grail for this method. When this condition is met, the entire energy spectrum of the system can be determined through a simple step-by-step algebraic procedure, completely bypassing the need to solve complicated differential equations. It's like being given a master key that unlocks every single energy level in one go. This approach has been used to solve famous potential models like the hydrogen atom or the harmonic oscillator with remarkable ease, revealing the hidden supersymmetric structure that has been underlying these textbook problems all along. Beyond its utility as a problem-solving shortcut, supersymmetric quantum mechanics offers a profound philosophical insight. It suggests that certain quantum systems we once thought were unique and isolated are actually part of a larger, symmetric family. A particle trapped in one potential well might have a secret twin, a doppelganger living in a completely different-looking well, yet both sharing the same rhythmic set of energy levels. This reveals a deep and previously hidden connection between different physical situations, a symmetry that isn't obvious from the outset but is uncovered through the supersymmetric lens. It teaches us that the universe often encodes its deepest simplicities in complex disguises, and that by learning its symmetric language, we can see through the disguise to the elegant structure beneath. Now, imagine if the key to unifying the fundamental forces of nature wasn't a new particle or a complex field, but something far more radical, an entirely new dimension of space hidden in plain sight. This is the brilliant and elegant premise of Kaluza-Klein theory, a classic idea that dared to suggest the laws of electricity and magnetism are actually the geometric shadows of a higher dimensional reality. Our story begins in 1919, just as Einstein was dazzling the world with his complete theory of general relativity, which described gravity as the curvature of four-dimensional spacetime. A little-known mathematician named Theodore Kaluza was captivated by this idea. He wondered if he could extend Einstein's beautiful geometric framework to include the other known force of the time, electromagnetism. His approach was breathtakingly bold. He simply took Einstein's equations and rewrote them for a universe with not 4, but 5 dimensions, adding one tiny, curled-up spatial dimension to the familiar 3 of space and 1 of time. The result was nothing short of miraculous. When Kaluza performed the mathematical expansion, Einstein's equations naturally split into 2 sets. One set perfectly reproduced the original equations of general relativity, describing gravity in our 4-dimensional world. The other set, to everyone's astonishment, turned out to be the exact equations James Clerk Maxwell had derived decades earlier for the electromagnetic field. It was as if by adding a single new dimension, the force of electromagnetism simply fell out of the geometry of gravity for free. But this immediately raised a pressing question. If there's a 5th dimension, where is it? Why can't we see it or move through it? The answer came from another physicist, Oskar Klein, a few years later. He proposed that this extra dimension isn't like the large, extended dimensions we know. Instead, it is curled up into an unimaginably tiny circle, a loop with a radius potentially as small as the Planck length. To understand this, think of a drinking straw. From a distance, it looks like a simple one-dimensional line, but if you look incredibly closely, you see it has a second, circular dimension wrapped around its circumference. In the same way, Klein suggested every single point in our familiar 4-dimensional spacetime might actually be a tiny, closed loop, a minuscule circle so small that it is completely invisible to all our experiments and senses. We are, in effect, insects crawling along the length of the straw, completely unaware of the circular dimension curled around us. This elegant mechanism provides a stunning explanation for why we perceive different forces. In Kaluza and Klein's 5-dimensional universe, there is only one force, gravity. But the way we 4-dimensional beings experience that gravity depends on how it vibrates within the hidden dimension. The component of the 5-dimensional gravitational field that vibrates along our familiar 4 dimensions manifests as the gravity we feel every day. However, the component that has a slight ripple in the tiny, curled-up 5th dimension appears to us as a completely different force, electromagnetism. The photon, the particle of light that carries the electromagnetic force, is interpreted in this theory as a standing wave of gravity trapped in the compact dimension. The symmetry of the circle, its rotational invariance, directly gives rise to the conservation of electric charge, one of the most fundamental laws in physics. In this view, the forces of nature are not separate entities. They are merely different aspects, different vibrational modes of a single, unified higher dimensional geometry. For a time, this was a magnificent and promising idea, a potential blueprint for a unified field theory. But it eventually fell out of favor, primarily because it couldn't incorporate the 2 new nuclear forces, the strong and weak forces discovered in the mid-20th century. The theory seemed to be a beautiful but incomplete relic. Yet, like a phoenix, the core concepts of Kaluza and Klein have undergone a spectacular rebirth in modern string theory. String theory doesn't just propose one extra dimension. It requires 6 or 7 of them, all curled up into the complex shapes of Calabi-Yau manifolds we discussed earlier. But the fundamental Kaluza-Klein idea remains the powerful engine. The physics we observe in our low-energy, 4-dimensional world is determined by the geometry and the symmetries of these hidden dimensions. Every vibration of a string, every particle we see, is a Kaluza-Klein mode, a specific way for energy to resonate in the higher dimensional landscape. The dream of unification through hidden geometry, first glimpsed by Kaluza and Klein, is now the central guiding principle in our most ambitious attempt to understand the cosmic symphony. But what if the very mathematical language we use to describe symmetry is itself in need of a quantum upgrade? For centuries, the concept of a symmetry group, a set of transformations that leave a system unchanged, has been perfectly described by the elegant structures known as Lie groups, named after the 19th century mathematician Sophus Lie. These groups provide the fundamental blueprint for everything from the rotations of a sphere to the internal symmetries of the Standard Model. Yet, as we venture into the quantum realm, where uncertainty and non-commutativity reign, physicists began to wonder if this classical notion of symmetry might be too rigid. Could there be a more flexible, generalized form of symmetry that emerges at the quantum level? This line of inquiry led to the creation of one of the most abstract and beautiful structures in modern mathematics, quantum groups. At their heart, quantum groups are not groups in the traditional sense at all. They are a type of non-commutative algebra that deforms, or Q deforms, a classical Lie group. The letter Q here is a deformation parameter. Imagine a dial you can turn. When you set Q equal to 1, the algebra behaves exactly like the classical symmetry group you started with. But as you start to turn the dial, making Q different from 1, the algebra begins to change. The key change is that the elements of this new algebra no longer commute. Their order of multiplication matters, introducing a fundamentally quantum mechanical flavor. This process doesn't break the symmetry, it gently bends it, creating a new kind of quantum symmetry that reduces to the familiar classical version in the everyday limit. It's as if we've discovered that our perfect geometric shapes have quantum resilient counterparts that can flex and adapt to the fuzzy nature of the subatomic world. One of the most profound arenas where quantum groups demonstrate their power is in the study of integrable systems. These are physical systems, often with many interacting parts, that have an unusually high number of conserved quantities properties that don't change over time. This makes them exceptionally orderly and solvable, even in the chaotic quantum realm. It turns out that the majestic symmetries underlying these systems are frequently described by quantum groups. They provide the mathematical framework that explains why these systems are so stable and predictable, acting as the hidden architects of order within apparent complexity. The quantum group essentially generates the set of commands that allow the system to be solved exactly, much like a secret cipher that unlocks the behavior of a vast network of interacting particles. The implications of this stretch even further into the deepest problem of them all, quantum gravity. In our standard approach, we try to quantize gravity, to take the classical, smooth geometry of general relativity and force it into the quantum framework. This has proven to be notoriously difficult, leading to the infamous non-renormalizable infinities. Quantum groups suggest a radically different path. Instead of quantizing gravity, what if we instead Q-deform the symmetries of spacetime itself? This approach imagines that the Poincare symmetry, the symmetry underlying Einstein's special relativity, which combines rotations and boosts, might actually be a quantum group at a fundamental level. In this view, the fabric of spacetime would have a tiny, inherent non-commutativity, a natural graininess that prevents those pesky infinities from arising in the first place. The hope is that by defining gravity not as a quantized force but as a theory whose very symmetries are quantum from the start, we might finally find a consistent and finite theory of quantum gravity, building the house on a foundation that is already quantum, rather than trying to retrofit a classical one. Now, if the no-hair theorem and black hole thermodynamics reveal a profound connection between information and area, then our next theory pushes that idea to its ultimate universe-wide limit. This is the holographic entropy bound, a principle that suggests the total information, the entropy, that can possibly be contained within any region of space is not proportional to its volume, as our intuition would suggest, but is instead strictly limited by the surface area of that region's boundary. It's a concept that turns our classical understanding of information storage completely on its head and provides one of the strongest arguments that we may indeed be living in a holographic universe. To grasp just how radical this is, imagine an immense, futuristic hard drive designed to hold the largest possible amount of data. You would naturally assume that its maximum storage capacity is determined by its volume. The bigger the box, the more super-dense memory chips you can pack inside. This is the classical, volume-based thinking that has guided physics for centuries. The holographic principle shatters this assumption. It posits that the ultimate information capacity of that region is actually dictated by the surface area of the box itself. No matter how advanced your technology, you could never store more information inside that volume than what could be encoded on its two-dimensional surface. The three-dimensional interior is, in terms of its information content, a projection of the data written on its two-dimensional boundary. The foundation for this incredible idea is the famous Bekenstein-Hawking formula for black hole entropy. Jacob Bekenstein's great insight was to realize that when you add a single bit of information to a black hole, say, by throwing in a particle, the event horizon's surface area increases by a tiny but fixed amount. Specifically, the area increases by an amount proportional to the square of the Planck length. This led to his formula: the entropy of a black hole, which measures its hidden information content, is exactly 1/4 of the area of its event horizon measured in Planck units. Stephen Hawking's discovery of radiation confirmed that this entropy was real and physical. This result was staggering because it directly linked information, an abstract concept, to geometry, a concrete, measurable property of spacetime. The holographic entropy bound generalizes this black hole result to any region of space, not just those containing a singularity. It states that for any isolated, weakly gravitating system, the maximum entropy you can pack into a region of space is also given by 1/4 of the area of its boundary in Planck units. Why is this the ultimate limit? Because if you tried to force more matter and energy, and thus more entropy, into that region than the bound allows, you would inevitably trigger a gravitational collapse. The region would become so dense that it would form a black hole. And what is the entropy of that new black hole? Precisely 1/4 of the area of its new event horizon, which would be smaller than or equal to the area of the original boundary you are trying to fill. In other words, a black hole is the most efficient information storage device possible for a given surface area. You cannot beat its density. Trying to do so only results in creating a black hole that embodies the very limit you are attempting to exceed. This bound suggests a breathtaking and fundamental symmetry between information and geometry. The universe appears to have a built-in regulatory system that prevents us from overloading any volume with information, enforcing a cosmic data cap that is set by surface area. This is an incredibly powerful constraint that has profound implications for our understanding of cosmology and quantum gravity. For instance, it places an upper limit on the total information content of the entire observable universe. We can calculate the area of our cosmic horizon, the distance light has traveled since the Big Bang, and the holographic bound tells us that all the information describing every particle, every force, and every event within that vast volume could, in principle, be encoded on a sphere at the edge of our observational limit. The holographic entropy bound is far more than a curious factoid. It is a guiding principle that challenges us to rewrite the laws of physics in an entirely new language. If the true, fundamental degrees of freedom of a system reside not in its volume but on its surface, then our traditional quantum field theories, which describe fields fluctuating throughout three-dimensional space, are effectively like highly efficient but derivative approximations. They are the emergent, effective description of a deeper theory that operates on a lower dimensional boundary. This insight is the very heart of the AD/S/CFT correspondence and other holographic dualities, providing a concrete mathematical framework where this radical idea can be explored and tested. It strongly suggests that to finally unite quantum mechanics and general relativity, we may need to stop thinking about spacetime as a volume and start thinking of it as a vast, dynamic information screen, with our rich four-dimensional reality being nothing more than a magnificent and incredibly detailed holographic projection. Yet if the holographic entropy bound reveals a profound limit to cosmic information, it is cosmic inflation that explains how that information, the blueprint for all structure in the universe, was first imprinted onto the fabric of spacetime. This theory posits a breathtakingly brief but pivotal period of exponential expansion in the universe's first fraction of a second, a hyper-stretching of space that not only solves several major cosmological puzzles, but also planted the seeds for everything to come through a mechanism of exquisite symmetry, near-perfect scale invariance. To understand why inflation was proposed, we must first look at the problems it solves. The standard Big Bang model, for all its successes, left cosmologists with some deep puzzles. Why is the universe so remarkably uniform on the largest scales? The cosmic microwave background, the leftover heat from the Big Bang, has almost exactly the same temperature in every direction we look. This is puzzling because without inflation, these distant regions would never have been in causal contact to thermally equilibrate. There simply hasn't been enough time since the beginning for light or heat to have traveled between them. This is known as the horizon problem. Then there's the flatness problem. The density of the universe appears to be incredibly fine-tuned to a critical value that allows for its continued expansion without either recollapsing or flying apart too quickly. The standard model offers no explanation for why this should be. Inflation elegantly resolves both issues by postulating a period of faster-than-light expansion driven by a repulsive gravitational force from a hypothetical inflattened field. Inflation takes a tiny, causally connected patch of the early universe and stretches it to a size larger than our entire observable universe. This process smooths out any initial irregularities, explaining the uniformity, and drives the geometry of the universe relentlessly toward flatness, much like how inflating a balloon makes its surface appear flatter and flatter. But perhaps inflation's most spectacular success is its explanation for the origin of all cosmic structure. According to the theory, the violent expansion of space was driven by the energy of the inflattened field. But like all quantum fields, the inflaton was subject to tiny, irreducible fluctuations, brief, random variations in its energy. These quantum jitters, which were microscopic and random, were suddenly caught in the act of inflation. As space expanded at a ferocious rate, these minute fluctuations were stretched from subatomic scales to astronomical sizes, frozen into the fabric of the universe as faint ripples in the density of matter and energy. This process transformed quantum uncertainty into classical density variations, providing the gravitational seeds around which galaxies and galaxy clusters would later form through the slow, relentless pull of gravity over billions of years. This is where the concept of scale invariance becomes absolutely crucial. The quantum fluctuations that gave rise to these seeds were born at a specific moment, when the universe was poised at a critical point, much like the magnet cooling on a knife's edge between order and disorder. At this critical point during inflation, the inflattened field was in a state where it had no preferred scale. The physics governing a tiny quantum fluctuation was identical to the physics governing a larger one. Because of this, when these fluctuations were inflated and imprinted onto the cosmos, they were stamped with the signature of that critical state. They became nearly scale invariant. This means the fluctuations in the density of the universe had nearly equal power across all measurable scales, from the size of a single galaxy to the vast expanse of a supercluster. A scale invariant spectrum is a specific prediction of the simplest inflationary models, and it is a direct consequence of the universe undergoing this period of symmetrical exponential growth. The evidence for this breathtaking prediction is written in the oldest light we can see, the cosmic microwave background, meticulously mapped by satellites like Planck and WMAP, shows a pattern of temperature variations that is the direct imprint of those primordial density ripples. The statistical analysis of this map reveals a spectrum that is almost, but not perfectly, scale invariant. It has a specific, tiny deviation from perfect scale invariance, which is exactly what many inflationary models predict. This spectacular agreement between theoretical prediction and observational data is one of the strongest pillars supporting the entire inflationary paradigm. It suggests that the largest structures we observe in the universe today, the great cosmic web of galaxies and voids stretching across billions of light years, can trace their origin back to subatomic quantum fluctuations, magnified to cosmic proportions by a brief but monumental period of expansion that was governed by a profound and hidden symmetry of scale. From the elegant dance of supersymmetric particles to the cosmic hologram projected from a distant boundary, from the infinite rebirth of cyclic cosmology to the geometric symphony of string theory, we have journeyed through a breathtaking landscape of ideas. Each theory, in its own unique way, points toward a universe that is profoundly ordered, mathematically beautiful, and intricately connected. These aren't just abstract fantasies, they are serious, compelling attempts to answer the most fundamental questions we can ask. What is the nature of reality? Why does anything exist? And how can the cosmos be both wildly diverse and deeply unified? The recurring theme, the hidden thread weaving through all 30 theories, is symmetry. It is the silent architect of reality, the invisible hand guiding the laws of physics from the first moment of the Big Bang to the formation of galaxies, stars, and planets. It operates on every scale, from the mind-bending non-locality of entangled particles to the vast, holographic encoding of information on the edge of the observable universe. These symmetries are often broken, hidden from our everyday view, but their influence is everywhere. They are the reason protons are stable, the reason light exists, and perhaps even the reason we are here to ponder it all. This exploration reveals that the quest for knowledge is far from over. It is more vibrant and exciting than ever. We are living in a golden age of theoretical physics, where ideas once confined to the margins of science are now being tested with powerful machines and precise observations. The Large Hadron Collider, neutrino observatories buried deep underground, and satellites mapping the faint whisper of the Big Bang are all part of a grand human endeavor to read the cosmic code. Every new discovery, whether it confirms a prediction or shatters a paradigm, brings us closer to understanding our place in this magnificent tapestry. The true beauty of this journey is that it belongs to all of us. You don't need a PhD to appreciate the awe and wonder that these ideas inspire. The simple act of looking up at the night sky and wondering what holds it all together connects you to every scientist, philosopher, and dreamer throughout history. It is a shared human curiosity, a drive to uncover the secrets of the cosmos. Now we want to hear from you. Which of these theories resonates most deeply with you? Was it the holographic principle that bent your mind, or the poetic cycles of conformal cosmology? Do you find the elegance of E8 compelling, or does the practical promise of the action captivate your imagination? Share your thoughts and your favorite theories in the comments below. Let's continue this conversation together, because the greatest discoveries are made when we dare to ask big questions and explore the possibilities, no matter how hidden they may seem.